Hi everyone, Ernie Tech here, and I'd like to get into the next part of our let's build a little mainframe using Sim390 and the Music SP operating system. Before I do that, I wanted to address a question or a suggestion that someone had mentioned in one of the comments, and that is, can I make things a little bit bigger, especially the console when you see the place you're typing in all the stuff into the mainframe? And the answer is yes, I can. What I've done is I put an entry into the configuration file for the emulator, and the entry is to rename and resize the default font that the emulator uses. So I've used the Lucida console from Microsoft. It's built into your PC, and I'm using an 18-point font, and it looks pretty good. So here's what it looks like. Let me crank up the emulator and me fire up a Model 4 terminal, and yeah, quite a bit bigger and much easier to see. So thanks for that suggestion. And I'm also taking out the awful little background ticking that I was creating. I thought that was cheeky, but it obviously wasn't, and I fully accept that has to go, and it did. All right, so here's what you used to say where I worked at, and that was, friends don't let friends do PowerPoint presentations. But yeah, here we are. The reason why I'm doing this is because it's a lot easier in the beginning stages if I show you exactly how emulation works as far as what a mainframe operating system expects. So if you're running MVS, MTS, Music SP, whatever system, whatever operating system would have worked on the actual big iron components, the things in the big room that made a lot of noise, made a lot of heat, that operating system has to believe that it's running on that. It doesn't know that it's running on a PC. That's the goal. And so what these emulators do is they create an environment where the operating system's calls, its system calls, are interpreted and responded to in such a way that the PC can handle it, and the operating system really doesn't know the difference. If it knows the difference, it's not a big deal. Anyhow, before we go onto this, look at this little thing. This is a model that a gentleman by the name of Nicholas Tamisi, he's on the webs, look him up. He's a model maker, and one of the things he wanted to make was this little IBM 1401 system from back in the day. That's the actual thing. That's his hand. He built this with cardboard, I guess, and plasticine sheets or plastic sheets, and he created this master modeler that he is, and I think it's great. Although it doesn't really qualify as a mainframe per se, I think, because it really wasn't, there wasn't really an operating system running on it. If you notice over here, that drawer was pulled out, and all those things right there were actually, I think, hard-coded for the purpose. And I loaded the cards in. The cards were then processed, and the work was done. Whatever happened, it was more hardware than software. So that was a 1401. We're talking about things that are of the S36070 ESA S390 lineage. So anyhow, this is the PowerPoint presentation. Bear with me on this. It's worthwhile for this one video to do PowerPoint. Yuck, I get it. But it helps to clarify what we're doing. All right, let me put the mouse over here and start this thing up. All righty. What's the goal? The goal is to make the thing on the right, which is the IBM ESA 390, what it might have looked like back in the day when this was running up at McGill University, to make that and the parts that we need, for instance, over at the pink side here, the 3390, the DASD drive, the CPU, the terminals, the printers, those are the hardware items that may have been at that location. That were the things that were there making noises and causing heat. The operating system has to think that's what it's working on. And these ESA 390 machines essentially were kind of the last vestige of the 370, and then after that, I think they were just called the Z systems. By the way, Z, as I have been told, stood for zero downtime. So if anybody wonders why they were called IBM Z system mainframes, it's because the zero downtime. You don't want computers that run the air traffic control system to go down. It's just one of them things that you would like to avoid if possible. What is this about? Again, the basis here is to bear with me, and then we'll get into the techie stuff, but this goes a long way. The guy who made all this happen was David Edwards, and he passed back in 2009. He was a employee of McGill University up in Montreal. And he had a lot to do with Music SP, the operating system. And when it was being phased out, my understanding is that he created this emulator that was designed really to run Music SP. And the emulator gave the machine, the mainframe, or the operating system of the mainframe, everything it needed to be functional on a PC. And it did that by virtualization. So in the little pinky area up there on the upper left, I know it's hideous. I'm not an artist. We're going to emulate the 3390 DASD, the disk drive from that hardware, using just a little file on the PC called musicxd.vol. That is a volume. That is where all the stuff is stuffed together. And there's a way to actually look at it through the mainframe, through music. And there's also a way to do it through an FTP browser or like FileZilla, because Mr. Edwards put a TCP stack into his software to let you actually connect to the emulator using more modern things like a web browser and FTP and things of that. Pretty cool. But anyhow, the files on your PC will serve as the virtual hardware. So instead of having a printer making a lot of noise, you're going to have a file called printout.txt in the same directory as all these things. It's all in one directory. And that's where the emulation will occur. And that's how this thing pretends that it's a mainframe. McGill University, this is where they created it. Interesting because university environments were very proactive in creating alternatives to the software that IBM was providing. And I think a lot of it had to do with cost. The IBM software was expensive, and the maintenance and the fees and the licenses go along with it. And they also wanted something which was more user-friendly because they were going to have terminals available for students and faculty, and they didn't need the robustness, perhaps, of MVS. It just was overkill for their purposes. So McGill created Music SP, University of Michigan created MTS, and a lot of other universities used them instead of IBM's. And the funny thing is that IBM over a while began to say, well, we can offer this OS along with our hardware and maybe license it as an alternative to MVS. And I think they had a better relationship once this thing actually got into the right hands. So that's why they created the academic versions of the mainframe operating systems, those being cheaper and easier to use for students and faculty alike. Okay. Here's where the fun started. So the 390 EXE is that single little file you double click, and it creates the environment where the operating system of your choice, in this case Music SP, thinks it's on a mainframe. That's the emulator. What it is, it's sort of a wedge. It's sort of a interpreter between the hardware of the PC and the mainframe operating system. The mainframe operating system really expects to be on the actual IBM hardware, the big stuff. And if it's not going to work. It just doesn't run. That's it. And if even were able to run, it would have complaints up and down. But what you need to do is they needed to create a system call interpreter, something that says everything that the Microsoft computer has, the little PC has, we got to make that available to the mainframe as though it was a mainframe piece of hardware. So we perhaps can't let it write directly to the laser printer because the drivers aren't there or it's just too incompatible. Because remember, a lot of things were built for the old reams of paper and the little sprockets on the side that were just ticking away all day. So what it does is it prints to a file that then you can open up with Notepad or something. That's kind of the way they did it. We don't have a set-aside drive on our PC just for the mainframe. So what they did was virtualization. It took a file, and they basically created like a zip file. They jammed it all into the file, and that file is being used in the same way that virtualization is used on a PC when you want to run a Linux program. It's the same concept. You're just using a virtual machine. So this is kind of a virtual machine. But instead of for Linux or something on a PC directly, it's for the operating system of a mainframe. That's how it works. That's all there is to it. And I say all there is to it, yeah, it was a big deal, but it's not magic. And what it does is it handles all those pieces, the interrupts, the memory, the access to the devices, and so on. And it does a lot of that at your direction through a configuration file. So here's what that looks like. So the configuration file is a text file in that same subdirectory as the the 390 EXE. And you put in there the definition of the things that you want the operating system to interact with. And you put them in there in such a way that they can mimic what was really in the actual, installation at your company or your insurance company. It's mimicking the actual hardware in such a way that the mainframe operating system doesn't know any better. It thinks it's in its real environment. Now, how this worked was pretty ingenious on IBM's part. IBM created so many different pieces of equipment, so many different versions of things, so many different finely tuned versions of operating systems. And they did it because there were so many different applications for mainframes. So, for instance, there was the kind of database intensive stuff where you have a lot of people interacting at kiosks or like the Department of Motor Vehicles. And so you have thousands and thousands of people entering in information and getting information back, and they all have to be maintained in such a way that there's no confusion. Each transaction happens perfectly or it doesn't happen at all. And then you have another environment which they created an actual operating system for, and that was for the air traffic control system. I can look that up and find it. I had it on the top of my tongue, as they say, but it was an actual name. It was called the Monitor. That's, I believe it was called. And it was an actual operating system just for ATC. So it was extremely tuned to that purpose and that purpose alone, and every airplane had a node. That airplane's node was changing at all times with the altitude and the heading and so forth, and so on and so forth. But one size didn't fit all. So the IBM sales engineers would go out and meet with the client, analyze their entire needs, whatever it was, and they would recommend and put together a package, a system, as it were, by choosing from all these parts. And in our case here, we have to take all of these things that might be available to us, or at least the very small subset that are available to us, and we have to define these in a configuration file so that the operating system, in this case Music SP, actually thinks that it's in the actual environment by the fact that the CFG file, this thing right here on the right, tells it everything it needs to know about where it's at. For instance, if we run down here along the side, you'll see the various things. I have the next slide will show you exactly what they are. What is this sort of akin to? Well, I'm going to say it's akin to the Linux rc.local, which is, I think, before they used systemd or something. That was the old-fashioned way of defining things, or the DOS config.sys. That was the file that was very, you tuned it. It was more than autoexec.bat. That was where your drivers were, and that's where software that needed to be loaded for particular devices were specified. Back in the day when we were running PCs with Novell NetWare, which I got heavily involved in on Token Ring, no less, that config.sys was highly tuned for that environment. And it's sort of like that, where you're creating a configuration file to tell the operating system or the emulator what it needs to know so that the operating system thinks it has everything it needs to function. I hope that's pretty clear. All right, on the other side here, on the right-hand side, this is what it looks like. This is obviously bigger. This was made in Notepad, so there's nothing to it. You just type it in there. And for the most part, it's already created. And what you do is look at the top down, and it's very easy to read. It says the memory assigned to this emulation is 8 megabytes. The console column's 80 rows by 300. Well, that just means that it flows off the side. I think the 300 is overkill. I'll go back to around whatever it was. Then they have auto IPL 201 blank command. What that means is that as a turnkey system, whereas we are just going to double click on the Sim390 exe and it's going to pop up and create the application, you don't want to do it manually. You want it all to happen automatically. So auto IPL simply means automatically load your instruction set to boot off of the device, in this case 201, and there's no arguments to that blank command. Go right to it. The next thing down was if you're going to connect by remote terminals, what do you come in on for TCP/IP, Telnet? 3270. You go down a little further. Everything in the mainframe environment has an assignment, a hex assignment, which is a location or an identification, a device ID of these various parts. So in this case, we're going to give device IDs to all the different potential connections with terminals, either your home or you're in the machine itself, or you're dialing in, well, not dialing in, but you're coming in over the network. Local 3270s are what happens right here on the machine in front of you through the emulator, which is where I changed the font size, and the remotes are where you come in from somewhere else. You could actually set up, if you had the computers in your house, a little subnet, and you could have one of the computers acting as a server, which was the mainframe, and you could have people log in. That would be fun. There'd be a party night, huh? So this is what it is to. This is the file that you use to define all these things. Also, there's in there. Interesting. It says IO punch device 00D invalid. That's because they didn't define a punch reader for the punch tape. They did define a actual tape, a reader though, 00C. There's a card reader or a tape reader. I don't know. I think it's a card reader probably. Also at printer at IO device right in the middle there, printer 00E printout.txt append. That's pretty interesting because that is the printer that normally would be sitting there chugging away in the building or whatever, where it was located, the big printer, the 1403, I think. And instead it goes to a text file and it appends the text file rather than overwriting it so you don't lose stuff. It can get pretty long, I guess, if you're really busy. But the address of that file is 00E, which is a very common address that you'll find later when we start playing with Hercules, which is a different emulator. So a lot of these things parallel each other. It's kind of a common thing. Way down at the bottom, the very last thing at the bottom, it says font for local 3270, font loc 3270, face name Lucida console, width, height. That's where I redefined the actual text so that it was bigger on that terminal so we could see it easier. And that's a lot easier than having to create a separate terminal and then change the font size on the separate terminal. So this actually worked out. This actually worked out pretty good. Okay, finally, and I apologize for the PowerPoint presentation because it's just not my thing. But anyhow, it works. All right, so a couple of things that will help us a long way to understanding how this works, to get it around your head so that when we move on to other things, other operating systems, other emulators like Hercules, it's going to make a lot more sense. So, for instance, if you notice on the right-hand side, that's the console. That's what is displayed to the operator, the administrator, you. And what it does is it says, okay, we've started, and we've gone through the entire process of loading up the operating system. So at 16.13, Music X on Unit 201, the system was loaded. That was the volume that was loaded. And then within that volume, there were pointers to other little sub-programs like PLPA and so on and so forth. A couple of little house cleaning things were done, and the system was initialized. So it says M092 system initialization completing, and so on and so forth. As you get further down the bottom, it shows the inetd, it shows the TCP/IP stack starting up, so you can get into it by FTP and HTTP and so on. And if you were playing with the thing and other people were on and off, it would actually show those terminals coming on and coming off. So that's what the console looks like. Another little tidbit so that you know what this all means is, what is IPL, initial program load. And all that is, it's similar to how you boot a PC. So an old PC has a boot track that they did back in the day, still do. And that's where it gets initial information to turn the hardware from just a bunch of rocks into the PC. So what it has to do is it has to say, okay, I have to find the starting point of that boot process. I know I'll go over to the volume called 201, and from that point, usually it's address 0. That's where I'll start, and then from there, everything should load up, and I become a full-fledged mainframe. And you think of it this way: let's say that you were a baker and you had a refrigerator full of eggs, and you had 10, cartons of eggs, and you were like me and kind of silly, and you identified the eggs as 0 through 9. That gave you 10, and you wanted to start with the first egg, and maybe the first one, which would be 0. So you would say, okay, carton 0, egg 0, that's where to start, and then go from there. Same thing here. We're going into volume 201, which was that file in the subdirectory where you have everything. And from inside of there, find your way to the initial starting point 0 and start booting. And if everything works as planned, you're in business. And that's exactly what happens. So that's the same process no matter what we're doing, whether we are on Hercules or this or stuff we haven't even discovered yet. That's the basis of how the mainframe starts. Very simple. in principle, but in reality, it's far more complicated than that. But that's how it actually will happen when we're doing it. Okay, a couple quick things. I want to thank whoever mentioned me to Hackaday, because I got on Hackaday, great website, actually highlighted this channel, even though I have very little content right now. Well, thank you very much. I really appreciate that. It really made my day. The other thing is I took off that crazy background noise. It wasn't worth it. Anyhow, that's why I did the PowerPoint presentation. Give us a grounding. I'll keep these to a minimum. We'll play with the machines and stuff itself, and a couple other little side tracks I want to make that are fun. All right. Thank you again. Please subscribe. Lots of stuff coming, and I'll talk to you soon. Bye for now.